Welcome, calculus fans. Calc 3 video on power series. So today we'll see what a power series is. We'll classify convergence of a power series via its radius and interval of convergence, and then we'll just discuss a few examples. So a couple motivating examples, and these examples sort of are generally how we will analyze power series. Test the series convergence as a function of x. So here we have a series, it's a function of x. It has some powers and some factorials. So just like we did before, we'll go ahead and apply the ratio test. So here we've used our usual simplifications on the ratio test, namely that m plus 1 factorial is m plus 1 times n factorial. X to the m plus 1 is x to the n times x. Simplify, simplify, simplify. See that a couple terms here cancel. And we can see that this limit takes on one of two values, kind of depending on what x is to begin with. Okay, so here we see that the limit is 0 if x is 0, and we see that the limit is infinity otherwise. So we say here that this power series converges only when x is 0. Okay, here is another example, motivating example, test the series for convergence. So test the series for convergence. The series is x minus 3 quantity to the n power divided by n. Again, with powers of n, we'll go ahead and use the ratio test. So we can see that when we take the limit as n goes to infinity of a sub n plus 1 over a sub n, simplify, simplify, cancel some terms, end up with a limit that goes to 1 times x minus 3. So, of course, this series converges when x minus 3 in absolute value is less than 1. It diverges when x minus 3 in absolute value is greater than 1. And remember that the ratio test is inconclusive at 1. So at those points, as it turns out, you just have to test individually. And we can do that by substituting the values for which x minus 3 in absolute value is 1. So that'll be 4 and 2. Okay, a quick typo here. I realize this series should be starting at 1. Nevertheless, when x is 4, we can see that this series is divergent because it's exactly the harmonic series. And when x is 2, we can see that the series is convergent. It's the alternating harmonic series. So here we would say that the series converges at 2 and not at 4, but everywhere in between. Okay, one more example. Here's one more example. Test the following series for convergence. Again, with powers of n and factorials, we'll go ahead and apply the ratio test. So here, simplify, simplify, simplify. Again, x to the n plus 1 over x to the n gives you an x. N over n plus 1 factorial, n factorial over n plus 1 factorial gives you 1 over n plus 1. And that limit, as it turns out, is 0 for all values of x. So here we would say that the series converges for all x. And these three examples, as it turns out, are they encapsulate all of the possibilities for power series. So in general, a power series that looks like the following: the sum n equals 0 to infinity c sub n x to x minus a to the n power. This is called a power series centered at a. One of three things can happen to this power series. It can converge only when x is equal to a, like the first one did when x was 0. It can converge for all values of x, like the last one did, or it can converge with some radius of convergence r. So in this last example, this capital R is called the radius of convergence. And testing at the endpoints of that radius, namely where the ratio test is inconclusive at x minus a get equal to r in absolute value, gives the interval of convergence. So generally speaking, when we analyze power series, we're interested in identifying the interval and radius of convergence. Okay, so just a few examples to illustrate finding the radius and interval of convergence. Here's the first one. Find the radius and interval of convergence of the series summing n equals 0 to infinity minus 3 to the n power times x to the n power divided by the square root of m plus 1. So we'll go ahead and apply the ratio test. Okay, so here, have a look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Simplify, simplify, simplify. Recognize that some of these terms cancel, like most of the x's and most of the 3's, and we'll be left with a value of 3 and a value of x and some square roots. Now, as it turns out, the limit of that quotient of square roots is 1, ratio of leading coefficients. So we're left with 3 times the absolute value of x for our limit. So by the ratio test, this series converges when 3 times the absolute value of x is less than 1, diverges when 3 times the absolute value of x is greater than 1. So the radius of convergence here is 1/3. Now, of course, this doesn't tell us what happens at the endpoints of the interval. The endpoints of the interval where x in absolute value is equal to 1/3, so where x is plus or minus 1/3. Now, of course, we can just substitute that to c. I'll leave it to you to verify that when x is equal to 1/3, we're left with a series that's convergent by the alternating series tests, and when x is equal to minus 1/3, we're left with a series that diverges by the limit comparison test. Okay, so here we're just testing an alternating series or a series with positive terms by our methods from earlier in the chapter. So here is the interval of convergence. The interval of convergence is minus 1/3 less than x less than or equal to 1/3. Okay, so again here the radius is r equals 1/3, and we can find the interval of convergence by testing at those endpoints where the ratio test is inconclusive. Okay, another example, power series. Here is another example of power series. Find the radius and interval of convergence of the series sum n equals 1 to infinity of minus 1 to the n minus 1, x to the n over n. So again, we'll start by applying the ratio test. So here we end up with the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute value. Simplify, simplify. Notice that the absolute value bars kill the minus 1 to the n powers. Of course, here we're left with something that cancels and leaves us just with x in the numerator, and the limit as n goes to infinity of n plus 1 over n is equal to 1. So here, the result of the ratio test is the value, the absolute value of x. This is a series, of course, that diverges when absolute value of x is greater than 1. It converges when absolute value of x is less than 1. So we can see that the radius of convergence r is equal to 1. Now what's left is to test the endpoints. So we'll test when absolute value of x is equal to 1, so at x equals plus or minus 1. So when x is equal to 1, we can see that we have an alternating harmonic series, which of course is convergent. And when x is when x is equal to minus 1, we can see that we have a harmonic series which diverges. So I apologize for the zoom issues on this slide. I forgot to press the lock button. But in any case, I'll give you a chance here to look at that whole thing once and for all. Okay, one last example, the radius and interval of convergence of the series n equals 0 to infinity x minus 2 to the n over n squared plus 1. So again, we'll start by applying the ratio test. So have a look at the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute value. Simplify, simplify, simplify. Recognize that most of these cancel out. Recognize that this limit is 1, and at the end of the day, we end up with the absolute value of x minus 2 as the limit. So we see here that the radius of convergence is r equals 1. Now what's left is to test the endpoints. So the endpoints are, of course, where x minus 2 in absolute value is equal to 1, which happens at 3 and at 1. So I'll leave it to you to verify that it converges at x equals 3 using the comparison test or a limit comparison test, whatever you like. And at x equals 1, it converges absolutely, so it converges. The interval of convergence, therefore, includes both endpoints, minus 1 less than or equal to x, less than or equal to 3. Okay, hope you've enjoyed this video on convergence of power series. Thanks for your attention, and we'll see you next time. Bye-bye.